This video is about computing inductance from the shape of a conductor. It's chapter 28, section 2 of the book. The material in this section is not really crucial to understanding inductors, but it does help a little bit in understanding how we can control inductance when we're either trying to minimize inductance of some wiring, or when we're trying to get a particular inductor for use in a circuit. Okay, there's a lot of formulas on the web and in books about how to compute inductors for various different geometric shapes. And almost all of them have the same general form, and that is the inductance is a constant times the length of the wire times some geometric factor g. So L is the length in meters. Mu 0 over 2 pi, mu 0 is called the magnetic constant, and this is by definition 0.2 microhenries per meter. That is, mu 0 over 2 pi is 0.2 microhenries per meter. So the interesting thing here is, first of all, that the length of the wire is really what matters most in determining inductance. If you want to minimize inductance, keep your wires short. Okay, the geometric factor comes in different ways depending on how the conductors are arranged. If we just have a single straight wire, G is approximately natural log of 0.95 times the length of the wire divided by A. So A is the radius of the wire. And you can see that this G is unitless because we're taking two lengths, taking their ratio, that's unitless, and then taking the natural log of that. If we have two parallel wires, then G is approximately, again, natural log of 0.78 D over A, where D is the distance between the wires. If we have a circular loop, then G is approximately natural log of 1.39 R over A, where R is the radius of the loop. And notice in all these cases, we have something that increases it if we've got, in the first case, long wire relative to its diameter, or to its radius. A large separation between wires increases the inductance, or a large radius to a loop increases the inductance. So keeping things small, keeping things close together, helps to reduce inductance. Okay, let's look at some more. So again, all these things are, impedance is mu 0 over 2 pi times the length of the wire times G. If we look at a coaxial cable, we have G is about natural log of B over A, where B is the radius of the outer conductor. So a coaxial cable has an inner conductor, that's the radius A, and an outer conductor, which is a sort of cylindrical shell around it, and the radius of that is the top part of this ratio here. If we look at a stubby coil, something that's just got a few turns but is very short, G is about n times natural log of 1.08 r over a. And for a long coil, G is approximately n times r over h, where h here is the length of the coil. Okay. Basic message from all these is that to minimize inductance, we keep the wire short, we don't coil it up, we don't try and make a large radius circle with things, keep things small. Now all these calculations have been for air coil inductors, things that look like this one, where the thing is just coiled up in air. If we want to get more inductance, we can increase, not just have a single layer to the helix, but have multiple helices sort of one around each other to get more turns within the same length. Here's another example of that. Another thing we can do is that we can add, so taking our coil, we can add, let's change colors, a core to the coil where instead of having air in there, we put a magnetic material. So if we could put a ferrite core or an iron core, some magnetic material that concentrates the magnetic field, we can get larger magnetic field for the same current, and so we end up getting a larger inductance. And that's very commonly done to get larger impedances, and they're often packaged, as this one is, in on a small bobbin. So this thing kind of looks like this, with the top and bottom plates of the bobbin there also being magnetic material, which means that the magnetic field that we get goes from between the end plates of the bobbin. You can also get ferrite cores that look more like this, with the coil wrapped around a central post, wires coming out, but the entire magnetic field now is contained within the ferrite material, and you get very little magnetic field outside your component, and that's useful for preventing electromagnetic radiation from your coil. If you need a really large coil, you can put many turns of a small wire here, and here it's using a laminated iron core rather than a ferrite core. And audio chokes, things that are designed for very large inductances, are often done this way. I think that's about all we need to say about how inductors are designed. You won't be designing inductors in this class yourself, but just using inductors that other people have built, mainly ones of this style, which have a coil around a ferrite core. So the next video in this series will be about using GNU plot to create Bode plots for inductors and circuits that use inductors.